Okay, welcome in everybody to our final video on the van der Waals force to review the things that we've put together. So far, we looked at the interaction energy for the van der Waals force as being made up of three components. Now the first is what we were calling the Keesom interaction. So we'll say that's what the K stands for right there. It's some constants divided by r to the 6. We could also then talk about the debye, a different set of constants. And finally, the London dispersion is another set of constants. So effectively, this is the most general form. If you have nonpolar molecules or atoms, this is the only term that matters, since these two will cancel out. But if you have two polar molecules, in general you need to consider all three. And so what we'd like to do is really roll all three of these into one phenomena, in which we say there's this one van der Waals constant over r to the 6. It's negative, meaning it's an attractive interaction. And this was actually done in the 1950s by Mr. McLachlan. And the equation that he came up with that models reasonably accurately these three different contributions to the van der Waals force is as follows. So this is an equal sign just referring to up above. Minus 6 kBt divided by 4 pi epsilon 0 r to the 6. That's a good start. Then, where this gets a little more dodgy, is from n equals 0 to infinity. So now we have this infinite sum. And we introduce this little prime there, which is to tell us the n equals 0 case gets an extra factor of 1/2. It's kind of a weird thing. But what we're summing over is the polarization alpha 1 and alpha 2, which we're going to say is a function of frequencies nu n and the imaginary number I. And this gets divided by the dielectric constant of the medium squared that the two are in. So you can also apply this to solvents or to different media that the two molecules or atoms might be sitting in. We would like to say this is also a function of the imaginary number times nu n. So nu n are going to be these different frequencies. And in general, we could write down an expression for the nu n in terms of the energy of the system. So we say it's going to be 2 pi kBt divided by h times n. So you have just the different n's of the different energy levels of the system. And you know we can combine h over 2 pi to be h bar. So it gets even simpler. It's kBt over h bar times n. So that's simply our expression. So these nus all have to do with the energy of the system. And we'll now take a look at expanding this infinite series to see if we can recover the Keesom, debye, and London energies. So to unpack that McLachlan expression, the first thing we want to understand is how is alpha, the polarizability, a function of the frequency nu, that which is the frequency in this case that the system is absorbing energy from the environment. So that's what nu I is in this equation. This is the absorption frequency of the atom. This is the frequency that it preferentially likes to absorb, or this particular wavelength. And so nu is the variable that we're varying, and you can see this kappa is part of the damped oscillator model, we're treating alpha as a simple harmonic oscillator. And the other expression that we want is going to be the alpha of a dipole. Talk about polarizing a dipole in not just the constant molecules and atoms. In this case, it's going to be the magnitude of the dipole over 3 kBt. Now that right there is exactly the time averaged energy that we derived from the Debye effect, missing the r to the 6 dependence, which would take it from the polarizability to the energy. But adding the frequency dependence looks just like this, where we have I nu divided by some reference nu. Here, again, that's a property of the material. This has to do with the relaxation of the electrons in the system. So with these two expressions, you can see both times that there's a nu in the equation. It's I times nu. It's I times nu, or in this case, it's nu squared. So in any of these cases, if we wanted to find alpha of a dipole of I times nu, or if we wanted to find just this alpha of I times nu, if we plugged in those i's, they would cancel with all the existing i's, or in this case, the squaring would get rid of the I, would give us just a -1. And so that's why we're saying it's a function of I times nu, because we actually want to, in some sense, make a real expression out of what we had. So let's return. In our previous expression, we just had one alpha. What it actually is the combination of this alpha for nonpolar objects and this alpha for a dipole. So we'll write down the total alpha right now.
What a beautiful face I have found in this place, circling all around the sun. What a beautiful dream that could flash on the screen in a blink of an eye and be gone from me.
So here we flip the orientation of the board. So we want to find alpha total as a function of I times nu. That's going to be simply equal to the alpha, plane alpha, which is of a nonpolar object, plus the dipole, also of I times nu. And what we get, what we can say for those two expressions is it's alpha 0 over 1 minus kappa nu over nu I plus nu over nu I squared. And what we're going to do is just index the nu's by n, since that's how it works out. And then the dipole contribution, magnitude of the permanent dipole, 3 kBt, 1 minus nu n over nu r. Okay, so we have this big expression, and it's real. So this is all good. We could plug this back into our McLachlan equation, and we'd have everything we need. These are all the constants that add up in the series. So the first contribution we want to find in the sum is when nu equals 0, which is also when n equals 0. That would just be the first term in the expansion, minus 3 kBt over 4 pi epsilon 0 squared r to the 6. Why is that a 3? We had a 6 up there before, and for some reason the first term gets multiplied by a 1/2. There's a reason, but we don't need to go into it. Now, what you would get from the sum over the polarizabilities is simply alpha 1 of 0, alpha 2 of 0. So we can expand the expressions that we got for those on the previous board as follows. So we pull down our favorite constants, just like that, and we would get the two terms. So here's going to be alpha 1. It's going to be p1 squared over 3kbt. And then we're going to get a plus an alpha 0, 1 from the dipole and from the nonpolar effects. And this is multiplied by just exactly the same thing with 2's for the other one. So what you can see is we, at this point, have indeed recovered the energies. The key sum effect comes from these two. There's the magnitude of the dipole squared over 3kbt. And the Debye effect, which had to do with inducing a dipole onto a polarizable atom or molecule, would come from these terms in the series. So what we have is effectively just the additive effect of Keesum and Debye. And it's from the higher order terms, where nu is non-zero, that we get the London effect. Again, that's a dispersion relation. It relates frequency to energy. So to track down the non-zero frequency terms, we'll say for nu greater than 0, it's a bit more complex. And the way to do it is to pass a sum over n to an integral over dn, which is a bit hand wavy because this is a discrete variable, 1, 2, 3, etc., and this becomes a continuous n. But if you say the n's are very small, then that approximation makes some sense. But what you get from doing that integral is exactly this. You get the multiplication of the alphas, factor of 2, r to the 6th, and finally h nu 1, nu 2 over nu I1 plus nu I2. So I meant to subscript these as I. So again, this is the frequency at which the atom or molecule ionizes. We previously wrote this as I1 times I2 divided by the sum. What we've just recovered is the London dispersion relation. Right here, coming out of the higher order frequency terms of the McLachlan equation. So that's it. That's a relatively solid and unified theory for the van der Waals force. And next videos we'll finally get to some of those other interactions, hydrogen bonds, electrostatic charge interactions, as we finish up this series.